Hello everybody, my name is Tevfik. Following my LinkedIn post for the stress-based casing design series, today I'm going to present the part number one, which is the mainly uniaxial burst rating. Before we get into the details, let's look at the von Mises yield criterion, which is widely used in the tubular design. And let's look at the equation. So the left-hand side is the yield strength, which is basically in this elastic region. That's the end of it. It's not the ultimate tensile strength, which is quite higher. We are interested in the yield strength. For example, for L80 pipe or N80 pipe is 80,000 psi. For P110 is 110,000 psi. So on the right hand side we have the principal stresses, tangential stress and the radial stress, which the derivations were made by Lame. And they are historically referred as Lame equations for the thick wall. And we have the axial stress, which is the tension or compression divided by the cross-sectional area, and to convert it to psi from pounds. And we have the also account for the bending, which is due to the doglegs in the web. So when we look at this equation, if no torsion is initiated, i.e. if we are not rotating the pipe for cementing, or let's look at the ERD case where you need to get the liners into the horizontal section. So you need to rotate to break the friction. Other than that, you will have no torsion induced. That's why we call this torsion. We neglect this, and it applies to many cases where no torsion is there. So it's zero. When we look at the direction of the stresses, so basically the name also suggests the direction. So there's the radial direction, there's the tangential direction, and then this is in the axial direction of the pipe. And here we have the design limits and the kind of a cross section of a pipe. You could see the cross section, and you could see the inner diameter and the outer diameter. So that wall thickness that we refer to here is the nominal wall thickness, and we are gonna touch base on that one when we derive the Barlow equation, because usually API accounts for the 12.5% of a manufacturing tolerance on the wall thickness. So you will need to use kind of a correction factor accordingly. And here we have the design limit plots. So we are gonna build a design limit plot on the part number 5 of this video series. And today for the burst rating we are covering the upper part, right? So that's the left quadrant here is the compression and burst. Right quadrant is basically tension plus burst. And you could see that these are all the uniaxial limits. However, on some sections the limits are a bit different. That's because of the axial stress is being considered with the triaxial analysis and not with the Barlow or the uniaxial rating. And here this one is as I mentioned, is the uniaxial rating. I set it as 1 at the moment. So this and then when you increase your design factor, it will tend to go down. And I draw some hypothetical lines here, and these hypothetical lines, they could extend here or they could extend there. And some companies, according to their casing design manual or standards, they will let the users to design a load case or a casing that extends into this triaxial area where it exceeds the uniaxial limits, or some companies might not allow that. So that depends on their internal guidelines. So when we look at the axis of this design limit, the y-axis is the delta P, that's P internal minus the P external, and the x-axis is kind of a tension or compression depending on the load state. So this side is the tension, this side is the compression, and plus the backup pressure, which we are gonna look a bit deeper on the part number 4. And the load cases that we are gonna test on part number 5, you will see that they will have kind of like a snake shape or a similar shape that will and each load case will have kind of an x value and a y value, delta p versus the tension or compression, and plus the backup pressure. So they will be drawn, and then we will compare how they look into the design limit plot. So I think we have covered a few things. So as I mentioned here, that's the wall thickness is quite important. When we say the outer diameter, the difference between outer diameter and the inner diameter, and then when you look at the book values for example, when you look at the data handbook, the green book, you will see all the wall thicknesses are nominal, and plus all on the spec sheets they will got the nominal wall thicknesses. Okay, so let's look at the burst equation, which is kind of a Barlow. So let me clarify, this burst equation is not a limit where basically the pipe will rupture. There are other equations in the literature for that one. However, API is kind of a Barlow equation is the widely known and solution, and also is quite practical to use, although it might set a lower limit. So it's the start of the yielding. It's not yielding somewhere in the cross section of the pipe. So the equation, as you know, is 2 times the wall thickness. That's the nominal wall thickness, by the way, and then divided by the outer diameter times the yield strength. Yield strength is this minimum specified yield strength, not the tensile strength. And then we basically correct it with a correction factor to reflect the 12.5% API tolerance on the wall thickness. So we will still use this equation. We will use the von Mises yield criterion to come up with the Barlow equation. So we know that the Barlow equation is not accounting for the axial stress. So we count the axial stress as 0. Radial stress is usually negligible compared to tangential stress or the axial stress. Negligible because it's smaller usually. So when we cancel the axial stress and the radial stress and plus the torsion, we come up with a yield strength is equal to tangential stress. So tangential is also called as hoop stresses in some sources. So in this equation, basically I just put the lame solution for the thick wall cylinder. That's kind of a inner pressure, inner area, outer pressure, outer area, cross-sectional area. That's 1 over r square. Depending on if you investigate the hoop stress or tangential stress in the inner wall or the outer wall, and then plus the differential pressure, inner area, outer area, and then the cross-sectional area. So because we know that usually the tangential stress is higher at inner wall. If you take the absolute values, we will solve this equation in the inner wall, which meaning that R equal to RE. And you will notice that in the Barlow equation you have the diameter, and then the lame solutions are radius. However, if I convert the RE square to the inner diameter square over 4, and then if I take the 1 over 4 into numerator and the denominator, they will cancel each other. So I will be writing them easily in inner diameter square plus the outer diameter square, which we will refer to as inner diameter and the outer diameter later in the series. So when we do this, we will we come up with a tangential stress is equal to inner pressure, internal pressure, times the inner area plus the outer area divided by the cross-sectional area. So let's not forget that one. Let's go to the second page. So we have we carried the equation from the first page, and then we put our wall thickness equation here, and then the wall thickness here, as you remember, is the nominal wall thickness. So we are going to replace the inner diameter with the outer diameter minus the 2 wall thickness, and then if we replace that one and then do the transformation, we could see that the outer diameter square, which is the outer area, cancels each other, and then you basically you are left with this equation. And then you could see that this numerator and denominator are same here. So I could separate this one, I could separate this one into two components. So that's the left component and that's the right component, which was basically, as you see, it was 1. So because this is a thin wall solution, it's known as a thin wall solution. DO over outer diameter over thickness, which is wall thickness, is greater than 1. So I know that this part is much higher than the 1. Therefore, I could easily cancel this one minus 1. So, and then also I know that because it's a thin wall solution, wall thickness is relatively small. I would also say that this 40 square is also can be negligible and considered as 0. Therefore, I'm left with 2 DO square divided by 4 times DO times wall thickness. And when you do the cancellations or division, you will come up with a DO over 2T, and then in order to find the internal pressure, which is the burst rating in our case, you will transform this equation into the yield strength times the 2 wall thickness divided by the outer diameter. Here, until now, that's the equation. However, we need to account for the API wall thickness tolerance, and we will account for it while putting a 0.7875, which is the 12.5% allowance. So in this equation, there is few things to consider. First of all, we didn't consider the axial stress, and also we didn't consider the radial stress as well, right? And then in this equation, you will need to look at the wall thickness, right? So for wall thickness, depending on the vendor, between the operator and the vendor, depending on the order, depending on the specifications, maybe you could specify a tighter tolerance on the wall thickness, and that will give you a higher burst pressure. Even you can request some specimen test to validate the wall thickness or increase the wall thickness or reduced wall thickness tolerance. So another things to consider during the life of the well is because we do the workovers and then we rotate the pipe across the tool joints across the casing. We don't know usually the casing wear. It's very hard to quantify, and also depending on the production, tubing leak, etc. Casing could be exposed to hydrocarbons, which we don't want. However, that could also affect the wall thickness of the casing. So when you do a corrosion log or something, then probably this value will be a better known measured value rather than a value that you predict on a casing wear, which is quite I think difficult. And also we need to think about the temperature rating. So the yield strength is also affected by the temperature, and I think the best point of contact is the vendor, depending on the grade or the specialty of the pipe. Either it's a chrome or a different grade of the pipe, H2S resistant pipe. You could get the temperature duration properties of the yield strength, and then that will impact the burst rating. And so we covered this one, that's the main caveat here, that we don't account for the tension in this one. If you remember the design plots, we do not the tension on the pipe or the compression of the pipe is not considered. So there's only the uniaxial part. Uniaxial limits is shown on the design limit originating from the Barlow equation. So on the right hand side, what I'm gonna do is the thick wall solution. This time we will consider the radial stress. We will not neglect it, and I will still call it the axial stress is 0 because it's a uniaxial rating. This formula on the top I will cover on the part number 4 because it will be long to look at this equation now. So let's take the equation as it is at the moment. So you have the axial stress, internal pressure, pressure differential, and you have the outer area and the cross-sectional area, which is equated to the yield strength square. So when we do the relevant interchange of the equations, for example, the cross-sectional area square, I could replace it by the basically outer area square plus the inner area square minus the 2 times inner and the outer areas. And when I do the equations, when I expand them, you could see that there's items here, 2 of them that cancel each other, and then here you will see that internal pressure square to the multiplied by the outer area square. You could see that there's 1, there's plus 4 is 5, and then minus 2 is 3, and then plus you have this internal pressure square times the internal area square. And after this one, what you need to do is to be able to compare or let's say make it alike by the with the Barlow equation. You will need to convert the AO square to the DO to the 4, because AO I could write it as a DO to the square. Pi's will cancel, so don't worry about the pi's. And then you could see, if you convert those equations, you could see that you come up with this equation. The yield strength to the square, that's cross-sectional area to the square, and then 3 times outer diameter to the 4, and then plus the inner diameter to the 4. And you take the square root of the yield strength, and then you could see that the internal pressure, which is the burst rating, will be equal to yield strength times the cross-sectional area divided by root square of this term. So in this term, you could notice that there is no wall thickness accounted. So if you need to compare the apple by apple, what you need to do is you need to pull the inner diameter to account for the wall thickness. So how do we do that? We need to account for the 87.5% here. Therefore the new inner diameter, when accounting for the wall thickness, will be inner diameter is equal to outer diameter minus the original wall thickness divided by 2, but we again multiply by 2 to get the inner diameter, so that those two will cancel, times the allowance. And when we look at this one, I just put a number for our interest. You could see that, for example, for 958 LAT 53.5 pounds per foot casing, we could see that if you use the Barlow equation, a thin wall solution, we get 79.7 psi. That's the book value, and then or the spec value. And then when we use a thick wall solution on this one, we will get a slightly lower value when we account for the